Okay, so same stuff with the chain rule, but now trig, which we didn't have any of last night on your homework. So, again, prior to needing the chain rule, anytime we took the derivative of anything trig-oriented, we only had the sine of x, or we only had the cosine of x, or the tangent of x, or I'll just get them all down, the cosecant of x, the secant of x, and the cotangent of x. So I'm going to first review those 6 derivatives, because these are the ones that we need to memorize. The derivative of sine is cosine. Sine is cosine. Derivative of cosine is negative sine. Those were the initial 2. And then we had that follow-up day on the Friday before break with all the other 4. So do you remember what was the derivative of tangent? Secant squared. What was the derivative of secant? Yep, secant x tangent x. What was the derivative of cosecant? It was negative cosecant cotangent, wasn't it? One more day back. Yep, negative cosecant cotangent. And the derivative of cotangent was negative cosecant squared. A negative cosecant cotangent. The tangent and the cotangent both are like the squared, but the cotangent is negative, right? And then the cosecant and the secant are somewhat similar. I always think the secant one is easier to remember, secant tan, and the cosecant one is cosecant cotangent, but the negative, kind of like the cotangent was the negative. So for memorization purposes, just drawing some connections like that, but at the end of the day, you have to know those 6. But again, we didn't need the chain rule because we were always taking the sine, cosine, whatever it might have been, of x. Now, with the chain rule, we're taking the sine or the cosine or the secant of more than just x. So in this case, we're taking the sine of pi over x, or not pi over x, just pi x. So to find the derivative of this, we're still going to approach it from the outside looking in, taking care of the trig issue first here. So the derivative of sine is cosine, so that'll be the cosine of pi x. But then we have to multiply that by the derivative of what's inside again. Okay? So what's the derivative of pi x? Just the derivative of this. Pi. Good. And oftentimes when you clean that up, especially if that's a constant, that's going to be more appropriately written out in front. So pi times the cosine of pi x is your final answer. Okay? On this one, we're taking the, and I'm just going to throw parentheses in there, we're taking the secant of x squared. So the derivative of secant is secant x tan x, but it's not x in this case, it's x squared. So when I take the derivative of secant, it's secant of the x squared, tangent of the x squared, and then we're going to have to multiply that by the derivative of what's inside. And Morgan, what's the derivative of what's inside? 2x. And again with that one, I'm going to bring my 2x out in front. Any questions on that? Okay, on this next example, we're taking the cosine of this piece squared. So, starting outside looking in, it's a trig derivative. The derivative of cosine is negative sine of this same piece times the derivative of what's inside. So what's inside is this binomial squared. How do we take the derivative of a binomial squared? What rule do we need? The chain rule, good. To take the derivative of just this piece, when we're multiplying by the derivative of what's inside, we need the chain rule to find the derivative of this. So again, we're going to bring the 2 out in front. That 2 exponent will drop to a 1 times the derivative of what's inside of that. So the derivative of 1 minus 2x is negative 2. So there's just these different tiers of looking inside the trig function. And then once you look inside the trig function, you have to look within that function, because there's a chain rule within that. So that's a chain rule within a chain rule. Okay, organization is the key here. So as far as reorganizing this, I'm always going to lean towards ending with my trig piece. So all of this, along with the negative sign, would be a coefficient of the trig part. So you've got a negative 2 times a 2, which is negative 4, times a negative, which would just be a 4. And then you've got the 1 minus 2x binomial. And then you've got your sine of 1 minus 2x squared. Any questions on that? Okay, on the next example, what do you see from holistically from the outside looking in? What rule, what type of derivative rule needs to be applied first? The product rule. Good. So we've got the first times the second. Okay? So when we go through our product rule, we have our first secant of 1/2 theta. First times the derivative of our second. Now the derivative of our second is going to require the chain rule, because I'm taking more than just the derivative of tan theta. It's the tan of 1/2 of a theta. So first and foremost, what's the derivative of tangent? Secant squared of 1/2 theta times the derivative of what's inside of that. What's the derivative of 1/2 theta? Just 1/2, good. So just to make this really clean, like so you can go back and see exactly where this all came from. This is our first times the derivative of the second, which required the chain. So to continue with the power rule, we need plus the second. I'm going to go down, tan of 1/2 theta. That's our second. Times, we need to take the derivative of the first. So what's the derivative of secant? Secant tan, so that we need secant 1/2 theta, tan 1/2 theta, times the derivative of what's inside, which is 1/2 again. So that, let me make that long enough, that derivative of the first also required the chain rule. Okay, so cleanup. In our first product, what's our coefficient? 1/2. And then what happens when we multiply secant of a half theta times secant squared of a half theta? Very good. Secant cubed of a half theta. And on our second term, what's our coefficient? 1/2. That's right here. And then we've got a tan of a half theta times a secant of a half theta times a tan of a half theta. Yeah, good. Tan squared. You see that you got two of those. And luckily they're both of a half theta, otherwise we wouldn't be able to do that, right? If one was the tangent of theta and the other one was the tangent of half theta, we wouldn't be able to condense it like that. But because they're both a half theta, and then we still have our secant of a half theta. Okay, so that's cleaner. And that might be the final answer. But if it's not, what else could we do to this to try to take it a step further? Right now it's a binomial. We've got our first term and we've got our second term. Factor out what? A half. They both have a half, and they both have the secant of a half theta. So if I take that out, the first term is left with secant squared of a half theta. And the second term is left with, I took this out and I took this out, is just left with plus tangent squared of a half theta. Any thoughts there?
Secant squared can be changed to tan. Tan of half theta, but that doesn't really do anything.
Secant squared, you said secant squared can be changed to tan squared.
No, just tan.
Just tan. Why?
Because tan x is equal to secant squared. But
not equal to secant squared. That's the derivative of tangent. We're definitely done taking derivatives. We were done with that up here. From this point forward, it's all cleanup. I'm thinking that maybe, and again, I don't memorize the other two, but I'm thinking maybe that's a Pythagorean identity of some sort. So just to kind of review those, we've got, this is the main one. This is the only one I ever remember. But if I divide everything by sine squared, I can come up with another one. 1 over sine squared would be cosecant squared. That's not the one we're dealing with. If I divide everything here by cosine squared, I'll get tan squared plus 1 equals 1 over cosine would be secant squared. So, if anything, we might be able to capitalize on this one just to clean it up a little bit more. We might be able to, we can replace our secant squared with a tan squared plus 1. So if I were to replace this with a tan squared plus 1, that would be tan squared of the 1/2 theta plus 1 plus the tan squared of 1/2 theta. Keeping this out in front the same. And then these two would combine. So it would just be 2 tangent squares of a 1/2 theta in there. So, where am I going to write it? Ran out of room. I'll write it over here. Equals. It's going to go sideways. I got the 1/2 secant of 1/2 theta times, I've got 2 tan squared plus 1. So 2 tangent squared of half theta plus 1. And I'd have to look to see exactly what the book did, but, and I'll do that while you guys are looking at another example. I don't have anything on the back. That's okay. On the next one, this is a little bit different because our pi t is not being squared, right? Up here, it was actually whatever we were taking the secant of that was being squared. This is the overall cosine being squared. So one way to rewrite this so that I think we have a better feel for what's actually going on is to take the cosine of pi t, but that whole cosine is being squared. For whatever reason with trig, when they want to square the whole cosine part, they always have put the squared right after the cosine. But it does mean the same thing as this, agreed? Where you take the value of this and then you square the value. Are we okay with that? Okay. So I think as far as when we're finding the derivative of this, I think that that's the better way to write it so that you fully have your head wrapped around what rule we should be applying first. If you look at this holistically, what rule? Chain, power chain, right? So this 2 is going to come out in front, so g prime of t. This 2 is going to come out in front times the 5 is going to give us 10. And we're going to leave our base the same. And it's technically now only to the first power, but I don't need to write that. Times the derivative of what's inside. Now the derivative of what's inside is the cosine of pi t. And that also is going to require its own chain rule. Do we follow? Because the derivative of cosine is negative sine of the pi t. But then we have to take the derivative of what's inside of that, which would be the pi t. And what's the derivative of pi t? Just pi. And one thing, and maybe you do it naturally, maybe not, but I do always try to accentuate when I'm multiplying by the derivative of what's inside by using an actual multiplication symbol. Because if I don't, and then a negative pops up, I don't want that negative to be perceived as a subtraction. Do you follow? Okay, so that's the reason I'm pretty adamant about putting those multiplication signs in there. If you don't put them in there, and you just use parentheses, and that's fine, and you realize that that's multiplication, fine. But that's why I do that with the multiplication sign, is so I don't think of that negative as a minus. So now overall, what's our coefficient? Negative 10 pi. You've got this 10, this negative, and that pi. Those are all your monomials. Negative 10 pi. So that takes care of all of that. And then the order from here doesn't really matter. Cosine pi t times the sine of pi t. That one was a little bit nicer than the last. Okay, any questions? Yes, Aaron.
Could you simplify that by doing the sine of 2 theta rule?
The double angle formula?
Yeah.
Yes, you probably could, because you'd switch this up into negative 5 pi times 2 cosine pi t sine of pi t. This is what he's saying. I hope for your sake that that doesn't happen, but you could. So 2 sine theta cosine theta is the same as sine of 2 theta, right? So it would be negative 5 pi, and this is a double angle. that's the same as the sine of 2 theta. But our theta in this case is pi t, so 2 times that would make it 2 pi t. I hope not, but you definitely could. Okay, he was capitalizing on the double angle formula. That was the formula he was kind of looking at, because he saw the cosine times sine. So he saw that. Could you put a 2 out in front? Yes, if you break up the 10 into 5 and 2, you absolutely can. But that would be tough to see. I don't think I would put that on there if I was choosing the multiple choices. Yeah?
Would it be a negative sign, because cosine is negative sign?
I'm not taking the derivative anymore.
Oh, okay.
The derivative stuff totally ends here. You really only do the derivative right at the get-go. And then from there on out, it's just simplifying. So I'll never, after my initial derivative section's over, I'm done with all of this. And then it's just cleanup. Okay? Alright. This one I like because it kind of highlights the difference between when you're squaring the sign versus when you're squaring what you're taking the sign of. So, for example, I would rewrite this as sine of x to the 1/3, and it's the x only that's being raised to the 1/3 there, not the sine. Versus on the second piece, it is the entire sine x that is being raised to the 1/3 power. Do we follow the difference there? Okay, so that kind of highlights what I was trying to illustrate before with the x squared versus something that would be like the secant of x squared, which would be written really like this. Okay, so it highlights that difference, you know, with a cubed root instead of a squared, but same idea. Okay, so when I take the derivative of this first piece, the derivative of sine is cosine, so it's the cosine of x to the 1/3 power times the derivative of what's inside. What's the derivative of x to the 1/3 power? Say it again, Owen. Yep, 1/3 x to the negative 2/3. Good. So there's the derivative of my first piece of my binomial, plus the second piece of my binomial. So like on this one, we did the trig derivative, followed by a chain. That's the trig derivative, followed by the chain. On the next one, it's going to be the power rule, followed by the chain. So I'm bringing the 1/3 out in front, keeping my sine x, but now that sine x is being raised to the negative 2/3 times the derivative of what's inside. What's the derivative of sine x? Cosine x. Good. So derivative stuff is over. From here on out, it is exclusively cleanup. On this first term, what's the coefficient? Just this first piece of the binomial. 1/3 really, right? But because I have this being raised to the negative exponent, I know that that's going to move to the denominator as x to the 2/3. And I'm going to have this cosine of x to the 1/3 up top. Plus, on this one I also have a 1/3 coefficient. This with the negative exponent is going to move to the denominator, so sine x to the 2/3, and then the cosine x stays up top. the only thing I think you could do is take out a 1/3. So we could take out a 1/3, and it would just be cosine of x to the 1/3 over x to the 2/3 plus cosine x over sine x to the 2/3. Yes, Dylan?
When are we supposed to like change this to square root and stuff like that?
You may see that this one is. You may see that that's written as the cubed root of x squared, and that's written as the cubed root of x, and that's written as the cubed root of sine x squared. You may see that.
So there's like no rhyme or reason to it?
You know, I really can't find a strict pattern between the multiple choice AP questions that I choose from and the way the book does. There's even a difference between that. Within the book, there is a difference between sections, so they're not very consistent about it. I will say this, if it's open response, I'm good with either. I would have to indicate to you that I want the final answer in radical form if I cared. Otherwise, I'll grade for both. So, as far as that's concerned, but again, if it's a multiple choice and you look at your answers and they're all in radical form, well then you got to change it to radical form and go from there.
Okay.
So I would look at your answers to give you a feel for that on a multiple choice. Does that make sense?
Yeah.
Same thing when you're checking, doing your homework and just practicing, you check the back of the book, all your answers are in exponential form, so then you can even look at that prior to getting started. What's the final answer? Do we have radicals? Because you're never going to remember that, right? It's not going to like skew your work. So as long as if you just look quickly and see if your aim is for radicals or exponentials, that can kind of guide you. Dan? I don't know. I haven't gotten that far yet. Oh boy, we're really cruising.
1 to 5. Actually, no.
That's a lot.
9.
Try this one on your own. Start with that first one.
They would just do 8 on the homework.
That's 10 problems.
If we do what?
Odds.
Oh.
That's a lot. We did 13 last
Oh,
time.
Right, there's 10 problems on this sheet.
Yeah, and we've only done 6 of them in 40 minutes.
Okay, so it might be a little bit longer.
I have a meeting tonight. I can't do it.
I'm sorry.
Yeah, I don't need to. Yes, Sam will be there with
Then you won't get full credit on your homework. That's okay. If you can't do it, then that's the consequence. No big deal.
Wow. I mean, homework literally counts for like nothing in this class anyway.
It's 10% of your grade. Okay, come on. Dan? Daniel? Work. Daniel's on my baby name list.
Really?
Yeah.
You should use it.
I like the full name Daniel, though.
He would never call me Daniel. They really don't.
They're the only ones. See, that's what happens with Dan. That's why I can't do it.
Why would you like Dan?
You can't feed his ego.
I don't not like it. I just really love Daniel. All right, do the problem. Oh. As far as finding the derivative on this one, what's your first rule that you're applying? Quotient. And then, so it's the bottom times the derivative of the top, minus the top times the derivative of the bottom. This one doesn't really even require the chain rule ever, does it? No. If you look at the second one quickly, I would first rewrite this as 2 times the cotangent of pi t plus 2, and this whole cotangent piece is being squared. So from the outside looking in, what's the first rule that's applied? Power chain, right? We're going to bring that 2 out in front, keep this the same, and raise it to the first power. Then we will multiply it by the derivative of what's inside. And when you're doing the derivative of what's inside, you're initially doing a trig derivative, but there's also a chain rule within that. Do we follow? Okay, so that's just the outline of that one. On this one, with a binomial, the first piece is easy. What's the derivative of 3x? 3. It's on this second piece where, now I'm going to treat that negative as a coefficient, so hopefully the signs will take care of themselves. From the outside looking in, what are they squaring here? Just the pi x. They're not squaring the cosine. So this isn't a power rule to start. This is just a basic trig derivative where we would take the derivative of the cosine, which is negative sine, and then multiply it by the derivative of what's inside. So then it's a chain. So your homework there at the bottom? Odds. Yep, page 137, 39 to 57 odds. It's 10 problems.